So we're starting chapter 2 of Biology 101, and this chapter is going to cover our chemistry unit. So starting out, we have Dmitry Mendeleev. He's going to be known as the father of the periodic table. He was born in 1834 in Siberian province of Russia, and he's going to die in St. Petersburg, Russia in 1907. He had the misfortune caused his family to move to St. Petersburg in 1848, so that's how he ended up in St. Petersburg. He moved to the Crimean Peninsula in order to teach and improve health because of a huge tuberculosis outbreak in 1855. He's going to receive a degree in and taught general chemistry at the University of St. Petersburg when he's there. He's presented first with a sketch of the periodic table in 1869, and then he goes through and revises that table in 1871 to look more like the modern periodic table that we have today. Next, we have Davy Medal in 1882 and Copley Medal in 1905, which are going to be nominated for the Nobel Prize of 1906. They're going to have an element that they created named after him, which is going to be Mendeleev. And that's going to be the periodic element 101 when you look at the periodic table. Now, going into the basis of chemistry, we're going to have to first understand what matter is. Matter is going to be defined as anything that takes up space and has mass. So everything is going to be made up of matter. It's going to exist in three different states. We have solid, liquids, and gases. Some people, they take it further and they talk about things like plasmas. In this case, we're just talking about solids, liquids, and gases here. Elements are going to be what that matter is. So everything's going to be made up of matter, and those atoms of matter are going to be a specific thing. So that's going to be your element. So all matter, living and non-living, is composed of these naturally occurring atoms. 25 elements are going to be essential to life. You've got the major ones, which are going to be the macro elements. These elements are needed in bulk and large amounts. So they're going to make up about 99% of the body's weight of an organism. This is going to include carbon, hydrogen, nitrogen, and oxygen, plus phosphorus and sulfur. Now, your four big ones, your four major ones, are going to be, I always say CHON, C-H-O-N, and that's the carbon, hydrogen, oxygen, and nitrogen. Those are going to be what make up the major 94%. Or 96%, sorry. And that's going to be for that body weight. So with these macro elements, you're also going to have trace elements. So you have macro and now micro for the trace. The elements needed for these trace are going to be in small amounts, and they're going to include, you can't see it on the screen, I kind of cut it off. Let's see if I can move it. No, can't move it, sorry. These are going to be iron, potassium, sodium, zinc, and calcium. So here it gives you a visual of these macro and micro elements. The macro or micro, remember, is going to be your trace elements. So it shows oxygen is going to be the largest component. You can see by looking at the visual picture, it's in kind of a greenish color. That's going to be about 65% of the body. Next, it's going to be followed by carbon, which is about 18.5% of the body. That is in gray. Followed by hydrogen, which is 9.5% of the body, around 10. You see that in green. Then next you have your nitrogen, which is going to be 3.2% of the body, and then the others. So that's going to be the rest of the elements that you see here. Still moving around, okay. So atoms are going to be tiny particles that make up the elements. They're the smallest unit of an element that you can see it displaying its properties of that element. So if you cut it down any further, it's no longer that element. It's going to consist of three different types of particles. You will have protons, neutrons, and electrons. The protons are going to be the positively charged particles that are going to be located in the nucleus of the atom, and they're going to have a mass of about 1 AMU. AMU stands for atomic mass unit. And so looking over here, you see the positive charged particles. So that's going to be these that you see here. So those will be your protons. Neutrons are going to be neutrally charged. They're also going to be found inside of the nucleus. They also contain 1 AMU. And so 1 atomic mass unit, and that's going to be the ones you see here that do not have a charge in them. So you put these two together, the protons and the neutrons, and this is how you get the atomic mass, by adding up the mass that both of these together will create. Now next you'll have your electrons. These are going to be negatively charged particles that are going to be found floating around in the electron shell, or sometimes people call it the electron cloud. And so you'll see you have one here, and you're going to have one over here. And so those are going to be your electrons, and they are on energy levels. They do have a mass, but it is going to be so small that we often refer to it as being negligible. And so you don't have to count that in with the atomic mass when you're taking the atomic mass. So you can simply say that it is 0. Know that it does have mass, it's just not a lot of mass, so you can neglect the fact it's there, so it's negligible. So inside the periodic table, these elements are going to be arranged by their atomic mass. So that's why atomic number, sorry. So that's why that atomic number is going to be important. And usually when you're looking at a periodic table towards the bottom, you will see the periodic table has that mass. Usually it's at the bottom, and the atomic number is either going to be in the top or top corner. So with the atomic number, that's going to be the number of protons that the atom has. Each element is going to have a specific number of protons. Now the number of protons and electrons are usually going to be the same. Move myself down. And that's going to be when it is a neutral atom. Now once they start to give or take electrons, that's when they become a positive or a negative atom. But usually they're neutral, and that's because the number of protons and the number of electrons are going to be the same. Remember, protons are positive, electrons are negative. So if you have 8 protons, you have 8 electrons, then that charge is going to be neutral. Atomic mass of an atom is going to equal the number of protons and neutrons that are going to be found in the nucleus. Now those are not always going to be the same. You may have 5 protons, and you could have, let's say, just random number 7 neutrons. And so those always don't come out to be the same number like the protons and electrons do before they start to bond. Now, the chemical basis of living and non-living things, you're going to have a system for naming and using symbols to represent these elements. This is going to be developed by a Swedish chemist called Jacob Berzelius in 1813. First letter of the element's name is always going to be capitalized. The second letter will always be lowercase. And so if it just has one letter, you'll just see, for example, oxygen will just have a capital O. Carbon will just have a capital C. But if it does have 2 letters, like cobalt, it'll be a capital C, lowercase o. Or in this case, looking at this picture, you see that the atomic number is going to be 12. You see the atomic mass, 24, and then you see that that elemental symbol will be capital M, lowercase g, and that's going to be magnesium. The only letter that is not going to be used in the periodic table element name or symbol would be a J. So J is not used. Isotopes. These are going to be atoms of the same element, but they have different mass. So they contain the same number of protons, but they contain different numbers of neutrons. So isotopes of the same element can have identical chemical properties, but their nuclear behavior is going to be different. So some isotopes are going to be what we refer to as radioactive. That means they emit particles and energy and are going to be used in things such as fossil dating, like carbon-14, or sometimes you might see it as C14. And as a diagnostic tool in medicine, for example, titanium-99 or TC99. So an example of different types of isotopes for an element can be seen below for carbon. So you see carbon-12, that's its normal state that it's found in. You have carbon-13, that's where it has 6 protons and 7 neutrons. And then you have carbon-14, that's the one used for carbon dating. It's going to have 6 protons and 8 neutrons. Ions are going to be charged particles resulting from a gain or a loss of one or more electrons. They can form positive ions, or what are called cations, by losing one or more electron, because remember, electrons are negative particles. So if it's neutral and you lose negative particles, then it makes it positive. It could also form a negative ion, which is going to be referred to as an anion, and that's by gaining one or more electrons. And that happens when elements will bond to each other. So the periodic table is going to be the tool that's going to arrange atoms by their atomic number and similar chemical and physical properties. An order of arrangement was developed by Dmitri Mendeleev in 1869 and later was revised in 1871. It was expanded even further in 1904, and that's going to contain the gaps for undiscovered elements. So if you look at a periodic table, even today, you will see some gaps there, and with some of them, they will go ahead and they will put a spot there, but they know that it has not been discovered yet, or for some of those, they've been created in a lab for a very, very short period of time, like a matter of milliseconds. And so this just gives you a view of Mendeleev's periodic table as he was starting to arrange it. That's 1869. This is upon further arrangement. He's starting to classify it a little bit more, break it down, put it in different rows and tables. And this is going to be 1871. And by 1904, it's starting to get a better, more uniform look to it. By 2016, the periodic table is going to be completely full at 118 elements with known chemical and physical properties. Now, 92 of these are going to be naturally occurring, and 26 of these are going to be synthetic. First synthetic was technetium, and that's going to be the TC, and that was discovered in 1937 by synthesis. First entirely synthetic was going to be cerium, and that's Cm, and that was in 1944. This is what the modern periodic table looks like today. Move myself over right here. And so this is going to give you a view of different elements that you can see. Now, looking at the periodic table, there are some easy things that you can learn from this. Now, to determine how many energy levels go around the nucleus, you look to see what row it's in. For example, row 1 contains hydrogen and helium going across. When it goes across like this, this means that there will be one energy level around the nucleus, and so that's where you're going to find the electrons. Row 2, which is lithium, beryllium, going on through boron down to neon. Those are going to have 2 energy levels around the nucleus. Row 3 will have 3 energy levels around the nucleus. And I think that you probably have picked up now on what's going on. Row 4 has 4 energy levels, row 5 has 5, row 6 has 6, and row 7 has 7. Now, lots of times we talk about valence electrons when we talk about things that bond. With valence electrons, easy way to figure out how many is going to be on the outermost energy level, and those are the ones that always interact with each other in bonding, is by looking at the column it's in. So now we're going to look at the top. So if it's coming down, hydrogen down through francium will have 1 valence electron. So it has 1 electron that it's going to use for bonding with other elements. In column 2, it's going to have 2 valence electrons. That goes down from beryllium to radium. Column 3 will have 3 valence, and then of course 4, 5, 6, 7. Those all have that number of valence electrons there that are able to bond with other elements. Once you get to 8, 9, and 10, all of these are only going to have 8. Now 8 is a stable number. You might have learned in high school 8 is great. 8 is what it's reaching for. It does not want to bond with any other element if it has 8 electrons in its outer shell. So these columns have 8. They usually will not bond with other elements. Now starting over with number 11, you're going to have 1 valence. Column 2, you're going to have 2 valence. Column 3, 3 valence, and so forth. Once you get to this last column here, the 18th column, that one's going to have 8 valence electrons, and those are going to be your noble gases. They do not bond. Now, Marie Curie is going to be an important female scientist. She's going to contribute to science and actually win the Nobel Prize. So her contributions is that she developed the theory of radioactivity in 1896, and she discovered radium and polonium in 1898. So with her accolades, she's going to win the Nobel Prize in Physics in 1903, and then she wins the Nobel Prize in Chemistry in 1911. Now, she is the first woman to win a Nobel Prize, and she's actually the first to win a prize twice, and the only person to win a prize in 2 different scientific fields, both physics and chemistry. Now, with the arrangement of the elements in the periodic table, I just showed you different groups and I showed you rows. So let's talk about that a little bit more here. With groups, that's going to be your vertical columns I showed you. That's going to indicate the charge of the atom and the number of valence electrons. That's what helps it bond. Remember, I told you that. That's the ones that are going to be on the outermost shell. It shows you periods. These are the horizontal rows that indicate numbers of orbitals where the electrons are located. And so basically, that's the ones I showed you that go across. Metals are going to be located on the left side of the periodic table, and they're going to carry a positive charge. Nonmetals are located on the right side of the periodic table, and they'll carry a negative charge when bonding. Metalloids are going to be divided metals from nonmetals and contain characteristics of both of those. And then you have your noble gases. These are going to be the nonmetals that have a satisfied octet rule. That means they have 8 electrons on the outer energy shell, and they do not care to bond with anybody. They're stable. And so taking a brief look at that, you can look around at the different elements here. Of course, you do have your exception over here. You have helium, which is going to be a gas, but it is located on the left-hand side of the periodic table. Now, electron configurations. This is going to refer to a number of electrons that's going to be found in the orbitals of an atom. Now, the first orbital of every atom can only hold 2 electrons, but every orbital thereafter can hold as many as 8. Example, sodium atom is in period 3, which means it has 3 orbitals around the nucleus, and it has the atomic number of 11. And because of this, the atom's neutral number is going to be 11. And not only it indicates the number of protons, but also the number of electrons as well. So these 11 electrons are going to be found within these 3 orbitals. So the first orbital will have 2 electrons. The second orbital will have 8 electrons, and then the third orbital contains the remaining 1 electron. Sorry. So here's some more different electron configurations. So it shows you hydrogen and helium. Then we go to period 2. It shows you lithium, carbon, fluorine, and neon. And then you go to period 3, and it shows you sodium, silicon, chlorine, and argon. So you can take a minute and look over those and notice how the electrons are configured. Now, the octet rule that we talked about is satisfying the octet rule is going to be done by obtaining 8 electrons in the outermost shell, or 2 electrons in the case of hydrogen, because hydrogen is going to be a special case. Noble gases are going to be extremely stable because they have 8 electrons in their outermost shell already. So these are referred to as inert, as they don't readily bond with other elements. Now, not to say that they technically don't ever bond, but they don't usually bond. So elements in families other than the noble gases are going to be more reactive, and they are going to strive to achieve a more stable electron configuration, and that is going to be 8. And so kind of like the noble gas configuration, they're going to want to bond with other elements so they fill that outer shell till they have 8, and then they become stable. So elements usually are going to react in such a way as they attain the electron configuration of noble gases closest to them in the periodic table. So elements on the right side of the table move right next to the noble gases. Elements on the left side backwards to noble gases to previous row. So atoms will gain, lose, or share electrons in chemical reactions to attain this more stable energy state through ion formation. This resulting ion formation is going to have the same number of electrons as the nearest previous noble gas atom. So metals will tend to lose valence electrons and form cations in order to obtain a noble gas configuration, example sodium. Nonmetals tend to gain valence electrons, forming anions in order to obtain noble gas configuration, such as chlorine. Let's see. Find somewhere to put me. All right. So chemical bonding. A chemical bond is going to be a force of attraction between two or more atoms of different types of molecules. The molecular formula is going to be the letter symbol for the elements and the number of atoms of each present. So, for example, H2O is water, NaCl is going to be your table salt, and C6H12O6 is going to be glucose. So H2O, it tells you that you have 2 hydrogens and 1 oxygen. NaCl, it tells you that you have 1 sodium for every chlorine. And table salt, that was with table salt, sorry. And with the glucose, it tells you that for every glucose molecule, you'll have 6 carbon, 12 hydrogen, and 6 oxygens in that molecule. And so you can look at those configurations and pictures below. With these, this is going to involve the valence electrons that help them bond and stick together. So the type of bond is going to be dependent upon the number of electrons in the valence or outer shell in the interacting atoms. And so that's what helps them achieve that octet rule. There's several different ways that you can write out chemical bonding. You can write out different things for chemistry. One way is referred to as the Lewis symbol. That's going to help to determine the number of valence electrons available for chemical bonding. This system was developed by an American chemist, Gilbert N. Lewis, in 1916. The way it represents the atom, it's going to use the element symbol in the center, and it's going to put the number of valence electrons around that symbol. So usually, hold on just a minute. Sorry, my computer wanted to restart. So with that, you have your element in the center, and then you're going to put the valence electrons around the outside, 2 on each side. So let me give you an example. If I had O, put an imaginary square box around it, and on each side of that box, you can only have 2 valence electrons. Starting from the top, 1, 2, 3, 4, 5. No, it didn't make it's not making my mark. So 5, 6. It's not cooperating today. 7, 8. So that's what you need 6, not 8. So that's what you see down there. Let me exit the drawing. All right, I was just trying to give you an idea. So that's why it looks like it does. You can only have 2 on each side of that imaginary box that's going around that element. And those are going to be made up of how many valence electrons there are. So preparing a Lewis symbol, like we said, place 1 dot on each side until there are 4 dots around the symbol. You can add a second dot to each side in turn. Number of valence electrons limits the number of dots where they can be placed. So each unpaired dot or unpaired electron of valence shell is going to be available to chemically bond with another element. Okay, so with this symbol, it's going to help to determine the number of valence electrons. Sorry, let's read another. All right. So the types of chemical bonds, moving on, we have covalent bonds. These are going to be where the valence electrons are going to be shared between one atom and another atom. Usually this is going to be between 2 nonmetals or 2 gases. These are going to be the strongest of all bonds that exist in nature. And each atom is going to achieve noble gas configuration when it does this. And so here's some of your examples that you can see below. The next type is going to be an ionic bond. This is where the transfer of one or more valence electrons from one atom to another. It's going to form attractions due to opposite charges of the atoms, and this occurs when valence electrons are going to be lost by a metal or a cation or positive charge, and these electrons are going to be gained by a nonmetal or an anion or negative charge. So each atom achieves noble gas configuration, and you can see this in the example or the case of sodium chloride or salt. Hydrogen bonds is going to be your third type of bond here. So the strongest was going to be your covalent bond, medium ionic. Now we're at the weakest, which is the hydrogen bond. So it's a weak chemical bond. It occurs between the slightly positive charge of a hydrogen atom and the molecule and slightly negative charge of another atom or molecule. So oxygen and nitrogen, either on the same molecule or different molecule here that you see. Difference in charges between the atoms is going to result in the unequal sharing of valence electrons in the covalent bond. And that's going to cause a positive and negative end or make them be polar. And we refer to that as electronegativity. Individually weak, but large number of them together can provide a great deal of strength. So this is going to be found between complex biological molecules, such as DNA. DNA will have a hydrogen bond that is going to be between the two ends of the DNA strand. And so we call those the sides of the ladder. And so the center portion will have your nitrogenous bases. Those nitrogenous bases will be hooked together. Let's say you have an A and then you have a T. They'll be hooked together in the center using that weak hydrogen bond. And it's important that it's weak because it's going to have to be able to unzip and open itself up and then reform very quickly. And we'll get more into that when we talk about DNA. So all living things are going to be composed of anywhere from 70 to 95% water. Now looking at the picture below, you can see these hydrogen bonds. These hydrogen bonds are going to be what are going to attach these molecules together. So the positive ends of the hydrogens are often attracted to the negative ends of the oxygen. And so that polarization there is going to help to attract and create that weak bond. Water also is going to have a very high surface tension. This is going to result from those hydrogen bonds that are going to be forming between those water molecules. They're able to kind of bend. They have a tension that's created through like a net-like property. So they kind of cross over and they attach to each other. And so that's going to allow for those bonds to be able to bend and not break. And so there's some animals that are actually able to use that property, such as this water strider insect that you see right here. And so they're able to actually use that to walk across water, or what looks like they're walking across water, by using the water tension there. Next property is going to be cohesion and adhesion. Cohesion is going to help the water stick together due to hydrogen bonds. Adhesion is going to be where the water sticks to other things. So think about that water bond going towards other surfaces. Cohesion is sticking to itself. So these properties are going to allow water to flow freely without molecules separating. This is going to be important in things like plants to help move water up from the roots towards the leaves. Some plants, for example, like the tallest trees, could be about 380 feet tall. So they're going to use these properties in order to get the water from the roots in the ground all the way up to the top leaves and the top branches, because all water that a plant uses is going to come from the roots and the soil. It could rain on it all day long. It's not going to absorb any of that water from any other part of the plant. It comes directly in from the roots and travels up to the leaves. Heat capacity is going to be another thing that water has. So high heat capacity. This is going to help to keep water liquid between 0 and 100 degrees Celsius, and it's going to be essential for the existence of life. So temperature of liquids is going to rise and fall slowly because of this high heat capacity. And basically the hydrogen bonds there between the water molecules are going to hold more heat and then help to release it slowly if it is hot. Now, if it's cold, it's going to take a lot of energy to come in and to warm it up. And so this is going to help protect organisms from rapid temperature changes. You don't want to walk outside during an ice storm or a snowstorm or really cold weather and freeze to death. The water in your body is going to help to control those temperatures. Same, you don't want to walk outside during a very hot day or be outside mowing or doing some type of activity, and then the water in your body rise too much, cause the temperature to rise too much, and then you die of a heat stroke. So it's very important that it has this high heat capacity in order to keep things level. Now we'll see this a lot in coastal areas. You'll notice that they don't get near as much snow as other areas, even if they are further north. And that's going to be because with these areas, all through the summer, that ocean is absorbing the heat, and it slowly starts to warm up. So as the temperatures change and it gets cooler, that heat's going to be released from the ocean, and it's going to keep those areas a little bit more temperate, a little bit warmer, and so they won't cool down quite as quickly, and so therefore they don't get as much snow and ice. Now when you get there early summer, let's say you made an early trip, you want to go in April, May, June, that water is still going to be pretty cold because it's going to take a lot of time in the sun as those temperatures are heating up to heat that large body of water. So usually it takes till end of June, July, August, September, that water's good, nice and warm. And then it will slowly release its heat to keep those temperate areas around the coastline nice and warm. It also, when it's frozen, will have a decreased density. So water is going to freeze at 0 degrees Celsius, and that's going to cause the water molecules to arrange themselves into a stable crystalline lattice. And that lattice structure is what you see in the picture below. That's going to distribute the water molecules further apart and cause the ice to be less dense than it is when it's a liquid. So when it's a liquid, they're all together and they can be really close together. But as it freezes, it causes them to spread apart. As it spreads apart, it becomes less dense, and so therefore it will float. This also causes bodies of water to freeze from top down, and it kind of acts like an insulator and helps protect the aquatic organisms underneath during the winter. It's also going to be a good polar solvent. So due to its polarity, like I said, the hydrogens are going to be slightly positive, the oxygens are going to be slightly negative. It's going to help it to dissolve polar and ionic molecules and help to break them apart. So that is referred to as dissociation. Nonpolar molecules, things like oil, are going to have neither a positive or a negative charge, and therefore it can be dissolved within it cannot be dissolved within polar solvents like water. So that's why when you try to put oil into water and shake it up, it might look like it's dissolved in there just for a short period, but then it will start to separate, so it does not dissolve it. Ionization is going to be a process in which pure water is going to be converted into an equal amount of electrical charge, hydrogen, protons, and hydroxide ions. So hydrogens we often refer to as bases. So hydrochloric acid, HCl. There's going to be an example, for example, with water though, it's starting with H. It is not going to be acidic, it is neutral, but most things, when you look at the chemical equations, it starts with H, you tend to know that that is going to be an acid. On the other side, if it ends in an OH or OH negative, that's a hydroxide, and those substances tend to be bases. So acids are going to dissociate in water and release hydrogen protons. Example, we just used hydrochloric acid. Bases are going to be molecules that release hydroxide ions, or they can take up hydrogen protons. So example, you can have an NaOH, and that's sodium hydroxide, or you could have NH3, and that can be ammonia. So pH scale is going to be something that we look at quite often when we talk about acids and bases. This is going to indicate the acidity or the basicity, or we often refer to it as the alkalinity, of a solution based on the concentration of hydrogen protons in a solution. It can range anywhere from 0 to 14, with pure water representing the neutral substance at a pH of 7. So that's going to be directly in the center. That's where neutral is. Acidic solutions have pH values that range between 7, with a pH of 0 being the most acidic. Basic solutions have values above 7, with a pH of 14 being the most alkaline or the most basic. So starting 7 neutral, anything below that 7 is acid, anything above 7 is going to be base. Now the further you get towards either end, either the top or the bottom, so for example 14 is going to be the strongest base, whereas 0 and 1s are going to be the strongest acids. So each unit on the pH scale is going to represent a 10-fold change in those hydrogen concentrations. So for example, soda would have a pH of 3, and then that with that 10-point scale or 10 times 10 scale, it's going to be 100 times more acidic than coffee with a pH of 5. Buffers are going to be chemicals that help to keep a pH steady and within normal limits of a living organism. It's going to help to stabilize the pH of a solution by taking up excess hydrogens or hydroxides. So for example, you have a carbonic acid buffer system that you see here below. If you take a real world example of this, maybe your stomach acid is too strong or it's causing you indigestion at a time, you could take things such as Tums to bring that acid up so it's not as acidic, and that would be adding into it. But your body's going to have a natural buffer system that's going to be able to do this on its own. Right, so that is going to end us for the chemistry section video. I will see you back for macromolecules in chapter 3.